Hi, this is Doug Smith, a verification engineer and instructor at Doulos. And my paper is entitled Doing the Impossible Using Formal Verification on Packet-Based Data Paths. And the reason why I say doing the impossible is because conventional wisdom tells us that formal is great for kind of like simple things like control paths, combinational logic, things that don't have really deep state that we have to unroll, things like bug hunting, interface protocols because they don't tend to span multiple clock cycles or many clock cycles. And for very specific applications, we find formal is really suitable and ideal for. And when we start to think about what formal is not so good at, we usually first think of data paths because data paths there's so many different possible combinations. Maybe you get into complex arithmetic. And then when you start looking at how many cycles that formal has to go through, we start to see that cyclical paths are not very good for it. Obviously, if you can't synthesize something, you can't use it for formal, and things that have really deep state space are not exactly ideal for formal. But having said that, why not run formal on packet-based data paths? Okay, it's true that a packet is very large. If we look at an example like Ethernet jumbo frames here, where you can get over 9,000 bytes, if you look at that, you think, wow, there's no possible way that that would work. In fact, the state space is something like 2 to the 72K, which obviously I'd agree with you if that was the case, if that really was the state space, then it is too much for formal. But the reality is when you deal with a packet-based protocol, you're really dealing with a small legal state space. In other words, we break things into different fields, and those fields only have certain valid values that are possible. And when you think about it, a packet is going to be parsed. So we are really looking at the header information and trying to decide, is this packet valid or where is this packet going? We may have conditional elements as part of that header. For example, to say whether this is, in this case with the Ethernet, is this a TCP? Is this an IP? Are we using tunneling? And that sort of thing. So really what we're doing is we're only looking at a subset of the state space here. And we're really looking at control path because we're using the information in the packet to control what the design's going to do. We don't really need to check the payload because that could be anything that we want to pass through this packet. So when you consider all that, you start to realize that even though this is a data path, even though this is an enormous state space, it's actually quite reasonable for formal. And to illustrate this, I'm going to look at a simple example, and that is one of using the CAN bus protocol. You can see that it's broken down into just a number of individual fields. And so this would be as a really good example for walking through the process of how we're going to break this down and use formal in order to verify this packet-based protocol. So the first thing we're going to do is model the control logic. And you don't have to do things in exactly in this order, but this is the order I like. And what I mean by the control logic, I'm referring to that handshaking that goes on between your design and whatever's interfacing to it. So usually in a packet-based protocol, we have some sort of start of packet signal and end of packet signal. In the case of the CAN bus, they refer to packets as frames. So you can see here in our code, we have a start of frame and an end of frame. And while the code here is not as important as the principle, the idea is that we'll create some sort of satellite code here to keep track of that we're in progress transferring some sort of packet, and then we'll write some constraints here just to make sure that it does the right thing. Next, we'll want to define the packet structure. We can try to define the entire packet using a struct and try to put it all into one, but when we do that, we're going to end up with a large number of bits. And you have to remember that formal is going to synthesize whatever we do. And so you will end up with probably a larger state space than what formal will like. In other words, the smaller we break this down, the better formal will be able to handle it, and the faster the analysis will be as well. So what I recommend is that we break down our packet into bits of 8, 16, 32 bits, and so on. Usually that's, formal can handle that, it's manageable. So we'll take a look at our protocol, and you can see here, like the data has 8 bits to it. So it's reasonable to say, hey, let's break this packet down into 8-bit chunks. And so that's exactly what we did here. And we illustrate taking one of the fields, the control field, and we're going to write a structure that represents it. Now, this is an example where one of the fields is less than the number of bits that we want to represent. So we have broken this into 8 bits, but there's only an IDE, an R0, and a DLC. So what we'll do is we'll add this extra unused bits in here just so that we can make sure that this structure comes up to 8 bits. And that's going to be important because you're going to see in a few slides that we're going to use all these structs inside of a pack union, so we have to make sure they're all the same. If one of the fields is larger than 8 bits, like we have here the CRC or even the arbitration, then what we need to do is to break it down into multiple structures. And that's exactly what we do here, is we take that CAN bus frame, we break it down into the different structs that we need to represent the different part. Here, for example, here's our startup frame. There was only 1 bit, and as part of that field, most things go unused. For the arbitration, we break that into multiple bits. For the CRC, we break that into multiple structs as well, and so on. Okay, now we have the structs defined where we need to put those structs inside of a pack union. This pack union will represent the different struct types that will make up our overall packet. And as you're well aware, if a pack union, everything inside of it needs to have the same width. And so we'll go ahead and put all these in. They're all 8 bits, but we'll also throw an extra member in here called qubits, just in case we want to flatten whatever is in here and just grab the 8 bits directly without having to worry about which struct or which type of struct that we're going to pick. And once we have that pack union defined, then we'll define an array for our packet. And we're going to also add an extra element on the end, and we'll explain why when we start looking at the constraints that we're going to use. We're going to need that extra element there on the end. So you can see here pictorially what we've done is we've created an array, and this array will represent our frame or packet of data. But we also need to keep information about the packet, about each of the elements in there. Now you can put all this into the same structure or the same packet array up here at the top, but when you do that, then you're making it more difficult for formal. It's easier just to split things into one array that contains the packet information and one array that contains the packet itself. So what we'll do is we'll define another struct here that will tell us what the different types of elements we have in our packet. For example, there'll be a kind field in here to say, is this a startup frame, or is it an arbitration, is it a control field, is it a data field, and so on. We'll also keep track of what the length of this particular field, because remember, not all the fields are 8 bits. Some of them are 8, some are smaller and less. So we need to keep track of that. And then we'll also keep track of the total length of how many bits so far, and we'll go ahead and create this second array here that will essentially sit in parallel, if you will, to our packet, and it'll give us the information to tell us about each element inside of our packet. Conceptually, here's what I'm talking about. So you can see that the packet represents the different bits inside of our packet or frame of the CAN bus. And down here at the bottom, we'll have information for each of these elements. So for example, the start of frame, it has a length of 1. And if we add up all these different bits, we have 54 bits from this point forward. Here we have 53 bits from this point forward, and so on. If we look at the last one here, there's 3 bits. So that's why this one has a length of 3 and a total length of 3. With the packet arrays defined, now we can start to write some constraints. And the first set of constraints we want to write are the constraints that constrain the information that we're going to be keeping for each of the elements. So we'll define a bunch of name sequences that have just some simple behaviors for us. In other words, we're going to be using sequence kind to set the kind of the particular packet. We'll use sequence total length, setting the length, and so on. And you can see that what we do is we're actually reaching into the next element of our array to grab its total length and adding it to the length of this current packet. And we've tried to illustrate this here so you can see when we pass in a 0, that goes into here, goes into the 0th element, and then we set the kind field here. And so that way, inside of our packet information, we know exactly what type of element this particular entry or index is inside of our packet array. If we take a look at our constraints in more detail, you can see here we're specifying n+1 to reach into the next element to grab that total length. So we've illustrated it here. You can see, for example, here at the very end, our IFS has 3 bits. So if we add 3 to the length of the element after us, we end up with a total length of 3. So we're really reaching into the next element. And this is why we need that extra element or index on our packet so that we can use our constraints and reach into it, because remember, everything's going to be synthesized by formal. And so these are really statically allocated, and you have to have all the elements or indices allocated in order for these constraints to work. So this whole ability of being able to reach into the following element or into the previous element, this allows you to pass information back and forth in your packet through your constraints. For example, let's say you want to be able to calculate your checksum or your CRC, you can reach back a previous element and grab the information, and that way you can do your calculations. Or as in this case here, we're using it to calculate the total length of our packet. With our packet info constraints defined, now we can specify what each field is going to look like inside of our packet. So for example, we'll create a property for each of the fields. Here's our start of frame. We know from the CAN bus protocol that the start of frame is always a 0. So we'll go ahead and constrain that. Notice here we have some unused bits, so we're just constraining those off to 0. You could leave those unconstrained. And then we can do it for all the rest here. So we're doing it for our arb high byte, also for arb low byte. And you can see we're just taking the ID member that we've defined here and assigning that into our packet. Likewise, the RTR here is the frame type. And again, this is an undriven variable. Both ID and frame type are undriven, which means they become formal control points, or what you might call a non-deterministic variable or random variable. So we're allowing formal to specify whatever value we want for that. Now we could have just left these unconstrained and formal would do the same thing, but this allows us then to write additional constraints if we really wanted to and control these outside of these properties here. With our field constraints defined, now we can apply those constraints. And we'll do that using a top level property that we're calling prop packet here. We'll pass into it n, which will refer to the element in the packet array. And then what we'll do is we'll look at each element, and based on what type it is, what kind it is, it'll determine what property, field property, will apply. And in fact, what we're going to do is we're always going to apply the property to the next element. So for example, here's our start of frame. We know that the next thing that comes after start of frame is our arbitration. So when we see a start of frame element, or field, then the next thing will be the arb high. When it's an arb high, the next thing will be an arb low, and so on. And what this allows us to do is we can use these conditionals here to really shape and control how we're going to generate our packet. For example, we'll let formal pick our payload size between 0 and 8. And so if it picks 0, then we know that there's no data field, but we do have a CRC field. So the next thing will be the CRC. If we do have something bigger than 0, then we know that the next field will be the data field. And then, of course, once we hit the last data field, then we know that the next thing will be the CRC, and so on. So this really gives us a lot of control so that we can decide which way we want to go as we generate our packet. I've illustrated it here so you can really visualize what I'm talking about. So let's say we have an assumption, a constraint here that sets the first element in our array. We're going to say the very first thing is going to be a starter frame, and that's why we pass 0 into this so that that gets applied here to the very first element. Then later, which we'll show on another slide, we're going to generate all these, or we're going to apply all these prop pack properties to our different elements. And so imagine if we apply it to the 0th element, then what's really happening is we're saying 0 plus 1, we're going to apply the prop arb high. So really what's happening is we're always applying to the next element in the array the constraint for the next element. So we start, we have to give it an anchor, we have to say what the first one is, and then we will apply the prop pack property to the rest of the elements so that it can go ahead and apply the appropriate constraints here as shown. Now let me show you how we'll apply all those constraints we just showed. So as we mentioned, we need to anchor at the beginning of the packet. So we'll say for the first element, it's going to be a start of frame. We're going to say for the last element, it's going to be of type none, meaning it is our terminal type so that we know that we're at the end of our packet. And then we'll use a generate loop to go through all the different elements of the packet array and apply our prop packet property. So this is saying that when we see the start of frame happen, we get the valid comes through, the start of frame goes high, then we'll apply these constraints to our packet. That will cause formal to generate the packet for us. And so if we have other calculations we need to do, for example, a checksum or a CRC, we can also apply those. So here we're using a function to calculate the CRC. And I would refer you to the paper to see the actual function. It's described in detail there. But this will use the packet, whatever's been set by formal, and perform the calculation and then pass that back. And of course, we can use that to set the, here we're setting a variable called CRC, which is also used in our formal constraints that are being applied up here from this generate loop. With all the packet constraints defined, the next step is to model the packet driving logic. What I mean by this is to model the logic that'll take whatever packet that formal comes up with based on what we've specified, and then drive it onto the bus or the bus interface of our design. Now, believe it or not, writing those packets is probably easier and more straightforward than modeling the packet driving logic. And that's because sometimes things get more complicated, as in the case of the CAN bus, we actually have bit stuffing that has to happen. And that's where every time you transfer 5 occurrences of the same value, you need to send 1 bit of the opposite. And that's not even shown here on this slide. But what I've shown is just the different modeling logic that you could use. And the real key takeaway here is you can see that we have 2 pointers. We have one that is specifying what element into our packet that we're going to drive, and then N here represents which individual bit we're going to drive out, because with the CAN bus, you're actually sending 1 bit at a time. So these are really essentially counters in here that are incrementing, and it's not important that you understand all that's going on here. You can refer to the paper and dig into the actual logic and look at the bit stuffing logic as well. But you can see here that we're using that P and that N, and we're using the flattened part of the packed union, the Q bits, to drive out one bit at a time onto our signal called transmit out. And then we are going to later take what's coming on the TX out here and drive it onto our data bus. We'll show that on a later slide. I think pictures can be helpful. So I've illustrated here what I showed you on the previous slide of what's really happening. So suppose we have our packet, it's already had the constraints applied, so we have the different fields inside the packet. Then the pointer P will select which element in the packet. Let's say we're going to select the control element. And so we get those 8 bits out, and you can see here's the different structure, or the structure that we defined for the control. And then we're going to take that in as the index into these 8 bits, and so we will send 1 bit out at a time and drive that onto the bus. And here you can see a waveform of this actually happening. We got the start of frame, and we start to drive out the individual bits from our packet. And you can see here's the different index pointers that are iterating through our packed array. On the waveform we just looked at, we saw that the output signal was called TX. But in our modeling logic, we called the output TX out, or transmit out. And the reason that we used a separate variable for the modeling logic was so that we could have more control of our output using the formal constraints. And here you can see why. What we're saying is when the packet is not valid, then go ahead and drive the output to be a value of 1. Otherwise, set it to what's on our transmit out signal that gets set by our modeling logic. So this just gives us additional flexibility here so we can come in with formal constraints and change things. Also make sure that when you're doing this that you tell formal not to change up your packet information while you're actually driving, because formal has a habit of changing things and doing whatever it wants to, trying everything. So you want to make sure to tell it to keep everything stable while you're doing your transmission. With that, everything is now set up and we can start to do our formal verification. So for this example, we're just going to use a cover property to generate a waveform so you can actually see this work. So we've specified what a proper transfer looks like. We have a start of frame, and then during that time we have packet is valid, and then we end up with an end of frame. And of course there's a few other constraints not being shown here that are preventing the end of frame from happening while this packet is valid. So then all we have to do is write our cover property or our assertion. So we're just going to say, go ahead and cover this, and it'll generate a waveform for us. Here's what a waveform might look like. You can see we have our start of frame, end of frame over here. We have valid happening the whole time. And you can see that formal has generated at the beginning of the start of frame what the packet's going to look like. You can see we have the start of frame, the arbitration, control, data, CRC, delimiter, ACK, EOF, and IFS here. And I've matched it up over here with our diagram. So you can just visually see what this thing is doing. And then what formal is doing is taking each of the bits inside of our packet array, which is not shown here. This is the packet info array, and it's driving them out here onto our transmit output signal. One thing I want to throw in here is so far we have been only looking at what are valid or legal packets because we've defined constraints that say this is what a valid packet looks like. What if we want to do error injection? We want to look at bad packets as well. Well, in that case, what we can do is we can create a variable here in enum for specifying whether the packet will be good or bad. And then what we do is we go back to those field constraints that we wrote and we break them apart so that we put the individual constraints for the field here in this top property, but then we create another property that calls it based on whether the packet is good or bad. And notice what we do here is when it's a bad packet, we simply invert the sense of the property. So that way formal will generate a field that does not match what a start of frame packet looks like. So this makes it very easy with just specifying in your precondition whether you want a good or a bad packet for formal to come in and to generate the packet you want, whether it has errors in it, whether it's legal or whether it's illegal. Lastly, let's take a look at results. I've personally used this approach on an Ethernet parser project before, and you can see that it took about a month of development to get this in place. But we found a number of design bugs using this. And of course, you're using formal, so formal can prove things. So that's really a really great advantage of using formal. And if you compare the fact that it took a month to develop this, it might take you a month to develop a UVM environment, but we were able to specify the entire Ethernet state space because of using this approach. Formal can go through and try every possible combination, but we know that it doesn't have to go through this enormous state space because we've told it what are the valid bits, and we knew that that's only a very small part of the overall state space. So this worked very well, and for this paper, for this presentation, I was able to whip out the CAN bus example within a week, and that was learning the CAN bus protocol as well. So this is quite doable, and it can potentially be done much faster than developing a simulation environment. And of course, you're going to be able to verify the entire state space. And so you don't have to go off and write all this test stimulus to do that for you. So I've summarized all the steps here, but check out the paper. It has all the steps listed out for you. So with that, I want to say thank you for listening and appreciate your attention. And I hope that this information will help you and you'll get to apply this on your project. So I would invite you to ask any questions that you may have. Thanks.